these statistics just by random error, by chance. I find that hard to understand how that would have been possible based on our results. In concluding, I want to show our success ratio of all the experiments that we ran, the ones that have excess heat. We find there's a definite grouping. The palladium boron material made by NRL is our most successful grouping. 7 out of 8 produced excess heat. The next successful grouping is Johnson-Matthey materials. Here we have, out of this group of material, we have 17 out of 28 experiments produce excess heat. So the question is, how could this grouping take place by chance? If we were making calorimetric errors and random errors, you would not expect to find this type of grouping. This shows that the palladium material is a very critical factor in these experiments. If you have good material, you get pretty good success rates for excess heat. But if you have bad material, we're going to the next one. If you have poor material, your success rate is poor. This is a NRL palladium, not the palladium sheet. We had some success. It's our intermediate 2 out of 5. But we had a lot of NRL materials that did not produce any excess heat. They also showed poor loading studies. Another source of the palladium. If you look through here, we have here no successes out of 19 experiments. So we have a definite grouping where we have poor material, and often this shows poor loading. We have poor success rate for excess heat. And it's hard to understand how this could happen by chance. How would we get this grouping if we're just making calorimetric errors? To me, it's almost impossible that we get this type of grouping. But it does show you the importance of the palladium material. Good material, you have good success. Poor material, you will have poor success. Co-deposition is experiments where you plate out simultaneously, plating out a solution and loading with deuterium in the process. Here we have 2 out of 34 that produce excess heat. This is a method by Stanisbach with another Navy laboratory. The reason we didn't get higher success, I think, is we had such a small volume of plating. Typically, we get 1 watt per cubic centimeter based on the plating volume. And this was a very small volume, so we would not have been able to detect it, even if the excess heat had been there, unless we were very high. We would have had to have 75 watts per cubic centimeter for this small amount of palladium in order to detect any excess heat. So I still think the co-deposition method is a valid method that should be further investigated. But you need a more sensitive calorimeter than ours in order to do that. In summary, we found excess heat for palladium boron alloys, a high success ratio. 7 out of 8 studies gave excess heat when we had boron present in the alloy. We found excess helium for palladium and palladium boron alloys. We did not find helium when we did the palladium cerium alloy. We found excess heat, but we did not get excess heat. This is two of the 33 studies where we did not get a correlation. But based on our results, we feel helium-4 is a missing product. It is a product of the process of the reaction. In all our experiments where we found helium-4, the helium-4 production rate always comes out very close to 10 to 11 atoms per second per watt, which is about the right order of magnitude. And finally, we have a final report on all the work done at China Lake, which just came out this last month, and it's being distributed. A lot of people may have already received this. I send out a lot of people to attend these meetings, and so if you don't receive it, let me know, and I'll send you a copy. This is the actual cover page of that final report. Anomalous effects in deuterated materials, and it's a government publication. This is the publication number NAWC-WPNS PP8302 if you want to request it from China Lake. So that is now available, which has all the details and complete report of all our studies. Okay, thank you.
Thank you, Mel. The paper is now open for discussion.
Very short question. First question is microphone. How can you explain the so high level of helium-4 as the background? Your background level is about 5.
Yeah, about 4.5 parts per billion. The reason we did that is when we did our original studies, we used vacuum rubber tubing to connect the cell and our gas sampling flasks. And helium does diffuse, atmospheric helium can diffuse through this heavy walled rubber vacuum tubing. And later when we went to metal flasks, we wanted to establish what our background really was in the previous studies where we used glass flasks. So we stayed with this heavy walled vacuum rubber tubing. And we've done calculations based on the time it takes to fill our cell with gas. You could explain the background by the amount of atmospheric helium that would diffuse through the heavy walled vacuum rubber tubing. You can also do calculations of diffusion through the glass, and that would have been much smaller. So most of our background comes from that heavy walled rubber vacuum tubing that we use to connect our cell and the sample flasks. And Ben Bush later has changed this and gone to a metal tubing in between. And I think he's got his background down to 1 or 0.1 parts per billion. So that's the reason for the higher background.
Here's a question. Can you give some explanation why the use of boron handling?
The reason
Because
for
boron is generally used to increase the amorphicity of the metals.
Yes. So your question is, why did we choose boron?
Yes.
Yeah. Well, one thing, some people have proposed that the process might involve boron and tan. Deuteron plus boron and go to helium-4. So maybe the boron is an impurity. Boron is always present as an impurity in both platinum samples, and it's also present in the glass. Most of these experiments run in Pyrex glass. Boron is in the glass, and it'll eventually wind up in the platinum. So boron is always going to be present anyway as an impurity. And so we wanted to actually put it there on purpose and see what the effect would be.
Thank you. Professor Ariani.
I want to congratulate Dr. Miles on excellent work. I also want to ask, I observed what looks like the periodicity in the generation of excess power, unless my eyes deceive me. They seem to be up and down, the same number of seconds per peak. Can you explain that now?
Well, part of the reason for that is we refill the cell each day. I think that causes some change in excess power. Also, when you fill the cell, then you dilute the electrolyte, and so that changes your voltage on the cell. And so your percent of excess power will change just due to that fact there, that you change the voltage applied to the cell by adding the deco and diluting the electrolyte. So that counts for some of the periodicity that you see there. You see it also in cells that produce no excess power. You can see the same kind of trend.
I also want to take this opportunity to make a general comment to everyone here. Please read the abscissa and the ordinate of volume figures, because it's very hard to read them from back here. They're very useful.
Okay, sorry.
Dr. Kucherov.
When you show the slide of excess energy dependence on time, at the very beginning you have a negative excess heat. Does it mean that at the initial stage you store energy, or it's within the experimental error?
It is experimental error. One of the posters we have later today shows an improved calorimeter that we have that can measure plus or minus 1 milliwatt. And you can actually see in the initial stages the heat of absorption of the curing going into the plating. When you look at the beginning stage of that, it tracks very close to zero. There is no negative effect really there. That is just experimental error that we saw there.
Final question, Dr. Kisaki.
I want to know the ratio of lithium-6 and lithium-7.
The ratio of lithium-6 and lithium-7. We just use lithium metal to make up LIOD. It's just from commercial suppliers, and it would just be whatever that was. I'm not sure what.
The PD sample is located on the bottom of the cell, and its mean temperature is read by thermocouple during the run without the applied electrical fields. The cell is completely machined in stainless steel, except for the lower side, the bottom. which is made of anodized aluminum in order to ensure the electrical insulation between the sample and the cell. Down the bottom of the cell, chamber allowing the flow of cooling water is we have a chamber allowing the flowing of cooling water in order to remove the heat due to Joule effect that we have when we apply the electrical field to the sample. Perhaps more clear scheme via a photograph of the apparatus is shown. In this picture, we see the two electrodes. The PV sheet is located along the line connecting the two electrodes at the bottom of the cell, while the central feed-through represents a thermocouple that can switch it off, disconnected from the external part. The mechanism we like to use to enhance the loading ratio, what I call the Stern effect, may be summarized as follows. This picture only region of the PV sheet is represented. The yellow part represents the gold coating at one end of the sheet. Normally, when the PV sample is located in the interior atmosphere, some gas penetrates the sample, following the so-called thermodynamical behavior absorption of deuterium into palladium. When an electric field is applied to the sample, the ions already present in the metal are forced to migrate toward the cathode. This way, lowering the concentration of deuterium in the central region that is not covered by anything. It's a direct contact with the deuterium atmosphere. This way, favoring further loading from the gas atmosphere. What about the spectrometric apparatus? It's a high-resolution mass spectrometer built by Hulbach, whose main characteristics are reported in this table. The important thing is the sensitivity of the instrument that has to be determined each time that we perform a measurement. So the values reported here are a rough variation range of the sensitivity that you can find during the operation. Since its importance, we performed several calibration runs before and after our measurements, obtaining for the sensitivity a value of 2.2 like 10 to the minus 4 ampere per milliwatt. That showed rather stable behavior with time of measurement. I shall now explain the experimental conditions that are summarized by this table and perhaps better by the plots below. The first column report the hours since the gas emission in the cell with the loading ratio performed after that time, the current applied to the sample, its duration, and whether gas analysis was performed. The last column reports whether some helium-4 presence was detected. On the plot below, the violet line represents the pressure, while the black one, the loading ratio. So, for a region of applied field are present, one after about 18 hours, one after about 65 hours, and so on till the end. On the down part, the lower part represents the two instants where a spill was performed. To say when some gas was extracted from the cell and subjected to mass spectrometric analysis. So the first 18 hours showed expected behavior of loading ratio when no electrical field is applied. The characteristics are first steep region followed by a smoother one leading to the asymptotic behavior curve green, while the black curve represents the mean sample temperature during this operation. Going back to this global behavior, we perform some two application of electrical field without doing any gas analysis, 1 and 2. After we perform an application of electrical field corresponding to a maximum current of 300 amperes, whose mean value, corresponding mean value of 175 amperes. In this case, helium 4 analysis was performed on the gas spilling from the cell about 1 bar, but we had no evidence of helium 4 presence in this case. At least we didn't find the helium 4 over 0.5 per thousand of the analyzed gas. The fourth regions, the fourth application of electrical field with a maximum value of 440 ampere, whose duration was about 25 minutes, was followed by a gas analysis and by a helium 4 signal that I will show next. It's perhaps important to briefly take a look again at the experimental apparatus, because first of all we have to talk about the blank measurements. So via the deuterium bottle, a controlled amount of gas can be put in this circuit, and after the opening of this valve, this amount of gas, in this case the 2.7 bars, are emitted in the cell. Of course, the cell is immediately closed in order to work. The rest of the gas stays in this part of the circuit. This way it can be spilled to the spectrometer part where a static measurement is performed. Static, I mean without any action of pumps. What we obtained sending the deuterium gas staying in this side of the circuit to the mass spectrometer was this, a peak corresponding to deuterium and absence of helium 4 in the region of interest. As I said before, no higher than 0.5 per thousand content of gas in the analyzed gas. After that,
Slides higher. When you put the slides on, can you put them a bit higher up so that we can read?
oh, sorry.
Vertical.
Vertical.
No.
Oh, sorry. So this is the analysis of the gas before analyzing itself. While repeated gas analysis performed after the application of the last electric field, the 400 ampere recorded in this table, so the last region, gave repeated presence of peak made as such. So in that expected region, we found a helium 4 peak corresponding to value of helium atoms of the order of 10 to the 18. I can give you the set number later, or something like this. What about the numbers concerning the age of these two peaks? The values obtained using the big aids and the sensitivity of the ISCMNS ID before showed helium production that enabled us to infer the number of atoms inside the cell to be 5.3 by 10 to the 18 atoms. Of course, any evaluation of the power production or power density production, mass or volume, can be made only if one has a precise idea of when the production of helium-4 has started. There are the possibility of soon production. It means that after 5 days of run of the cell, the helium production could be started very soon. In this case, the total time involved is 5 days, and it corresponds to a production of 1.2 by 10 to the 13 helium atom per second, corresponding to a power production of 46 plus or minus 7 bar. But if one considers the possibility, the hypothesis that the production has begun between the two last measurements, let's say a very short time, 21 hours. Of course, the helium production rates are higher, and so is the corresponding power production. These values can be made in comparison, put in comparison with the values shown in ICCF-6 in Monte Carlo, where we obtained 7.5 by 10 to the 16 for atoms, while in this case we obtained a number that's 100 times as large as about 100 times larger. The differences between the two measurements were the fact that in those measurements, in the old one, there was a pump present during the measurement, while in this case the measure is completely static. That's why. That's also the reason why we didn't give any error about these measurements. So the conclusion that we can at the moment reach twofold. From one side, a high value of loading ratio around 0.8. It's of course a mean value, as we have any information about the local concentration of deuterium till now. And second, so it seems clear that you're in fact reducing the duration the loading ratio above the thermodynamic limit. But the most important is the production of helium-4 from the two gas-loaded systems that could create variants of nuclear fusion reactions in other sheets. The future work we are going to perform mainly devoted back first of all, of course, to repeat such helium-4 measurements. But after all, systematic study of the two systems is necessary, and very important shall be the local measurement of loading ratio via resistance measurement during applied field, and the local measure of temperature also. Later on, we think we will vary the geometry, meaning perhaps using more bigger samples. That's what's thank you.
Two questions. One is, I mean, you earlier found some neutrons you claimed, and presumably there's helium-3 with it. Now, previously you said you found neutrons. and neutrons are produced with helium-3. Now, did you look for helium-3 for that reason, and also for the reason I explained earlier that Schwinger said you should look? The second question is, do you believe in the compound nucleus model? Because in the compound nucleus model, you form the compound nucleus in 10 to the minus 23 seconds in reaction time, and it lasts 1,000 times longer, up to 10 to the 20 to the minus 20 seconds, when it disintegrates. And it is so long that it's forgotten how it's formed, and therefore it always decays in the same branching ratios. And the same branching ratios says you should have 10 million times as much helium-3 as helium-4. This is another good reason for looking for helium-3. But you should also have 10 million times as much neutrons as you have helium-4, which is contrary to your earlier observation. So, do you believe in the compound nucleus model?
Sorry, the last time.
What kind of question is that?
Do you believe in the compound nucleus model? And here, just an answer.
What has got to do with that we compound model with your
Each question each time, please. Each question each time.
What's wrong with that with the matrix?
So,
What kind of questions are those? I don't understand.
okay, first, one of the first exercises I showed you was going to the description of the two bodies whose interaction. So the apparatus.
Please. Later you make your question. Now,
The apparatus was built to detect neutrons. If I find that right, the slide I give you also the number of neutron emissions. What I said before is that the neutron emissions were too low when compared with the reported excess heat reported by other experiments. We performed several experiments on titanium shavings and on titanium sponge and on palladium cylinders. Sometimes we had flux with a very good significance, but these numbers were too low to justify to be consistent with excess heat reported by that experiment. So that is mainly the reason why we decided to go to the second reaction involving the helium-4 production. I never talked about helium-3 production, and we actually can't perform such a measurement. I mean, an gas analysis in order to find helium-3 is not possible without instrumentation.
Next question. Okay, comment. Short comment.
Let me address to what the dog is opposing. See, we are looking at these reactions, assuming that these occurs. But there are many other possibilities, like let's say DE electron going to a certain state. And once you start looking into those new processes, which none of the theoreticians looked at or none of the experimenters considered, then there are other scenarios which might occur. So you cannot really object experimental data just based on conventional reactions.
That's right. That's right. These are the only two reactions we consider.
Now, Professor Okamoto, please. And
please let me know how carry out the long-term loading ratio measurement. Have you some good idea to make?
Yes. As a matter of fact, we did this kind of measurements in the older version of our apparatus, and the results we brought to Monte Carlo did discuss this point, because with that low power value, we were able to measure loading ratio via a measurement of electrical resistance. In that case, the electrical resistance was a mean value taken reading a voltage between two electrodes. Our purpose for the future is to put through three, shall I repeat very shortly, to perform 3 measurements of electrical resistance along the PD sheet in central position and near the ends. So along the PD sample, upside, consider the system will plate the ends where.
Okay. We might to discuss on this point. For this, you should enlarge your sample size.
Sample
Should be larger. You can.
No, for the moment we plan to continue with such sizes. First of all, perform this measurement. After we go try to scale.
Kojima and after.
Do you measure or have a role to measure regions in the experiment?
That's why I didn't indicate the third direction.
Okay, so please back.
I think your early measurement is just a thermal cycle of titanium or palladium, right? And now you added electric current. And then I think it's very important to measure the helium-3 or neutron again, because if you measure the neutron again, then you can really know the ratio between the neutron emission and alpha emission. And then I think it is very important to know the mechanism of these things.
We did perform neutron's measurements during the test we reported at ICCF-6 in Hokkaido. We reported there a value of 0.4 neutron per second per gram during that run, those runs, showing on the other hand a helium-4 presence. So we did consider possibility to go on with measuring net neutrons.
So coach, please.
The figure you gave of the EU4 produced is very high, 10 to 80. This means about 10 megajoules produced. I have no idea of the time you have this production. Can you give some
explanation for this fact?
And also, you observe some differences between the positive pole and negative pole of uranium.
It's physical. Okay, I shall firstly answer to this last question because I have a slide showing what the PD sample looks like after the run. It's visible. This part is the part connected to the cathode. So, of course, it seems that a higher value of temperature has been reached in this region. Concerning the values I reported.
The gold is in both, yes.
Yes. The ship is always gold plated at both ends. Concerning the numbers I gave, about the power production, the only thing we can do is stress again is to make some hypotheses. Only a precise knowledge of the duration of the production of helium-4 can allow to determine and consistent rate and consequently the power production. What was the question? Sorry.
I think in case of neutron, it's easy to diffuse in place, and
So
it's easy to diffuse. So in case of helium signal you observed, did you observe the disappearance of that signal after release of
electric.
I'm sure you want to know if this is one of the big I showed you. This was made after an electrical field application whose duration was reported to be about 25 minutes.
What's the left scale?
Sorry.
Please, what's the left scale?
Oh, this is an arbitrary scale. As a matter of fact, it corresponds to the millivolts of signal output. Sorry.
No, I don't want to interrupt.
While the peak I showed you before concerning calculation looked like this. So the red reports the helium, the deuterium peak, while the other two, while the green report the helium 48. This length measurement was performed before any application of electrical field.
How about after?
This was the measurement performed after the application of electrical field.
After that measurement, did you observe the disappearance of signal of
Ah, you mean the behavior in
by
time?
diffusion of
No, there were several peaks repeated in time. This, for example, is peak number 4 of the scan performed. Several peaks about
If you switched off the current,
after switching off the current.
Yes, the measurements were made after the field had worked. I mean, the field worked, the current was switched off, and it is simple, the current was switched
I
off.
think it must be disappeared with time.
No, excuse me, I shall briefly explain how we did. Otherwise, we don't understand each other. The spiral extraction of the gas to be analyzed from the cell is performed opening this valve, putting the gas in this region of the circuit, and after spilling an amount, controlling amount here, this valve, into the analysis volume. So when we did the test with electrical current, we simply applied electrical current after having the current being switched off. We closed the valve and we performed the gas analysis. Is that the answer you need?
I would like to make a question. Thank you. How long the result works? So means if you continue to feed current and gas, actually, you have like a constant production of helium-4, or after some time the system is self-destroyed. And one question before, did you use the gas before the palladium plate? The sheets? Okay. This is the important point for some helium stored from some long time.
Yes, we did that operation. And what is the fact that vacuum circuit was the gas heating all the parts of that. So if you analyze the gas before and after, you are sure to analyze the homogeneous gas.
And how long the system can produce helium-4?
Well, about the duration of time, it's
how long you perform your experiment? Hours, days?
about electrical current.
Yes, and the production of helium-4.
The longest field applications lasted 2 hours. Was one of the first, but in that case we didn't perform gas analysis. The other was a fraction of hours, so the first was 24 minutes, the second was the third 1 hour, and the last 24 minutes.
Why you stop experiment? Reason technical or just?
You mean after this?
Yes, possible.
These are very recent results. They were performed last week in they ended but at mid-September.
Thank you. The next one, but here is one, Carlos Sanchez.
Did you say
formation of cracks in the sample or any constitution?
Well, we observe systematically some deformations on the TV sample along its major axis. I mean, perpendicular to its major axis. Such kind of transverse ondulations between the two ends of the sheet in a number of about 20. This is a systematic thing we always see in our sample. From it means if you one looks at the lateral sides of the TV sample, one observes a situation like this. It's not precise, of course, but this number is about 20 ondulation along the leading length. This is the only mechanical fact that we can note, we observe.
Okay, we take it again, and so the next talk.
Now we have the final talk for this morning session. Study of excess heat and nuclear products with closed-control electrolysis systems by Yasuda, Nikita, and Takahashi. It will be presented by Mr. Yasuda.
The aim of this work is to study the correlation between excess heat by heavy water electrolysis with halogen cathode and deuterium-related nuclear products, namely neutron, helium-4, and tritium, in order to prove the existence of the new class of nuclear reaction in metal deuterium system essentially, and find a solution to the mechanism of possible reaction, the simultaneous in situ measurement of loading ratio, excess heat, and nuclear products with their correlation must provide us key evidences. In the present work, the overconversion ratio, excess heat, and nuclear products were tried to measure simultaneously in situ in a closed heavy water electrolysis system. To carry out accurate calorimetry, a newly designed closed electrolysis cell, which enabled heat measurement by using the mass flow calorimetry method, was manufactured. With this system, 7 experiments have been done by different cathode materials. This shows a cross-sectional view of a newly designed cell. This cell has relatively large volume, 738.4 plus minus 4.1 cc, so that the electrolysis can be carried out with relatively high input power, namely several 10 watts. The cell vessel is made of stainless steel coated with Teflon, and the spiral copper cooling pipe was raised around it. Temperatures at the inlet and the outlet point of cooling water were measured with chromium-argon thermocouple. Output is calculated from the difference of these temperatures and the flow rate of cooling water. The jointing part of plumbing equipped with the lid and a space between the lid and the vessel was sealed with copper gasket. Therefore, loading ratio of deuterium could be determined by measuring the change of D2 gas pressure of upper cell volume. Upper cell is here. The air at the beginning of mounting was evacuated and replaced with this gas about the 3 atmosphere. And even small quantity of helium-4 generated continuously or intermittently during electrolysis can be stored without losing for many hours. By sampling the upper cell gas after the electrolysis is done and analyzing it by the quadrupole mass spectrometer, the production of helium-4 can be detected. This is experimental system using the closed electrolysis cell. The cell was put in a stainless steel dewar to insulate from heat the outside. The cooling water was pumped up from thermal control bath, which is controlled with plus minus 0.1 Kelvin accuracy, and cooling water was circulated in a cooling pipe through a flow meter and discharged to the bath. A helium-3 proportional counter is set up inside polyethylene blocks beside the dewar to detect neutrons. This is a table for a summary of experimental conditions. 7 experimentals have been done using a 0.2 mol lithium OD electrolyte and plate palladium cathode. Several precondition palladium cold work annealed with or without copper surface layer were used for the cathode. The palladium cathode used in experimental 3 was annealed for 10 hours at 900 degrees centigrade with the heat furnace and was cooled down by the rate 10 degrees centigrade per minute. Palladium cathodes in experimental 5 and 6 have been already annealed before experiments. This is the summary of results for measurements of loading ratio, maximum values, excess heat, neutron, helium-4, and tritium. As regards to excess heat, in the run of experimental 4 and 7, excess heat up to approximately 4 to 5 watts were produced with the cold work and copper layer cathode and only cold work 1. However, during excess heat, nuclear product neutrons were not observed over the 3 sigma limit line of background level. In a pure mass spectral analysis, slight increases of helium-4 peaks were observed. However, helium-4 might not absolutely increase because it was difficult to calibrate the mass spectrometer to deduce total amount of helium-4 from samples. The next, I will state about experimental results in detail. This is variation of excess heat and loading ratio as a function of time in experimental 3. In the run of experimental 3, between 120 hours and 140 hours after the start of electrolysis, excess heat looked coming out. However, it was within the 3 sigma level of 99% confidence. 3 sigma equals 3.9 watts. Whenever anomalous excess heat was not produced, heat balance was at zero line, as looked like this figure, except that from 120 120 to 140 hours interval. This is variation of excess heat and loading ratio as a function of time of experimental form. Excess heat were produced from the time when input current mode was changed to the stepping up. Maximum excess heat exceeded 3.5 sigma level of the standard deviation and therefore very confident. Then D over palladium ratio were observed here to be almost constant in spite of the drastic change of currents by stepping up. However, this MCS data in experimental form shows that during the excess heat, neutrons as a nuclear product were not observed over the 3 sigma limit of the background level. At 4 hours after electrolysis starts, count rate were over 3 sigma. However, since the neutron source facility, Octavian, near our experimental place, was eventually running at the same time, and skyshine neutrons were thought to shower. Increase of neutrons might not be due to generation of neutrons from the palladium cathode. This is variation of excess heat and loading ratio in the run of experimental 7. Electrolysis by the stepping up mode was continued for about 200 hours using a cold worked palladium cathode supplied by Tanaka Precious Metal Corporation. Excess heat with 5 watt max were observed with maximum P over palladium ratio equal 0.90. For about a day, we stopped electrolysis and changed to the low 1 ampere, high 4 ampere mode with 6 hours duration per each of low or high mode was done for about 240 hours. Then, low high mode electrolysis technique was fully used by the open system study group of our laboratory. Excess heat were observed, but not over the 3 sigma level, and then loading ratio were higher than those of experimental 4 as a whole, but changed periodically in average from 0.82 to 0.87, corresponding to the current changes of the low-high mode. The next these are mass spectra of deuterium sample gas in experimental 3 and experimental 4. Judging from this diagram, used original deuterium gas was regarded to be contaminated very slightly with helium-4. However, in experimental 7, helium-4 peak was not observed with the same deuterium gas sample of used D2 gas cylinder, probably because the sensitivity of quadrupole mass spectrometer was getting worse than before. These show results of mass spectra for gas samples from from the upper cell in experimental 4 and 7. In these analyses, ion currents of helium-4 peaks were observed with meaningful increases compared with one of the original sample gas. Content of helium-4 in the sample gas from the upper cell was concentrated to be about twice through 3 times of the beginning of diesel gas. After about 1 through 2 atmosphere, diesel gas was absorbed to parachute plate. So, amount of helium-4 peak increases in experimental 4 and 7 should be regarded as marginal levels. It is necessary to calibrate quantitatively the mass spectrometer and fix the total quantity of helium-4 from the sample. In all the experiments, clear increase of tritium in electrolyte were not observed. This shows results of tritium analysis in experimental 2 through 5. Tritium activity of electrolyte before electrolysis was defined as background and one after it as foreground. There was difference in tritium level between that of experimental 2 and those of from experimental 3 to 5, because electrolyte was exchanged to new one after experimental 2. Tritium concentration during the long electrolysis would be suggested because of selective absorption of lighter isotope, namely H and D to parachute plate. In conclusion, in the run of experimental 4 and 7, excess heat up to approximately 4 to 5 watt were observed, and then DO parachute ratio was observed to be almost constant in spite of drastic change of current in experimental 4. However, during the excess heat, nuclear products, neutrons, were not observed, and clear increase of helium-4, tritium, and clear increase of helium-4 and tritium were not observed either. As regards to mass spectral analysis, because it was necessary to calibrate correctly mass spectrometer and fix quantity of helium-4, generation of helium-4 could not be definitively concluded, although visible increases of helium-4 peaks were observed for 3 cases of upper cell gas. Because of limited number of experiments, the correlation or non-correlation between the generation of excess heat and nuclear products cannot be confirmed. Now the 2 cells are running simultaneously in order to establish the more confident measurement system. Study the correlation of excess heat with the degree of loading ratio, D over project using different precondition cathodes, and hopefully identify the correlation of excess heat and failure for generation. Thank you.
Well, if I sat down here, I could ask some questions. And you've built a very nice calorimeter, and you've asserted some rather conservative limits on the accuracy of the calorimeter. I would have thought that the performance of the calorimeter would have been very much better than the standard errors that you've assigned. How did you determine the standard error of the calorimeter, the intrinsic accuracy of the calorimeter?
classical collaborate. And we made a calculation number and from using nickel cathode and measure the fluctuation of inlet outlet temperature difference and also the fluctuation of flow. And we estimate the standard deviation for temperature deviation and also the flow rate deviation. And after we sum up according to the Gaussian scale rule, and we estimate about 3% in conservative sense.
I think it's a very conservative error.
Yes, that's right.
Morris.
Thank you. Well, just, I think it's a very good way to calibrate it, look at the fluctuations. Anyway, my question was, what is the size of the palladium piece that you used?
Size of what? Tritium piece.
We used two kinds of plates. One is the about 2 inch by 2 inch, 1 inch by 1 inch, I'm sorry, and 1 millimeter in thickness. The other is the
1 inch by 1 inch.
yeah, and 1 millimeter in thickness. Yeah, the other is the half of the half inch by 1 inch and 1 millimeter in thickness. Two kinds.
Where is the value from?
From manipulations. This is the how we can display the details. We will discuss.
You tested 2 cathodes with copper plating. Was the plating on both sides of your palladium or only on one side?
Both sides.
Thank you.
Do you have a plan to find whether there's any palladium and hot helium in your palladium from the into the cathode material? Do you have a plan to take some of the cathodes and see if any helium is trapped in them in the future?
We have done already that measurement, but we didn't show this time because we have a problem with helium leak from outside when we elevate the temperature of the furnace. So we have already results, but we have some unguessed results because of the leakage problem from outside. We tried already.
You said that you have not observed any significant neutron burst in your experiment, and you said that the neutron count per hour.
Yes.
It seems to me that your employed dwell time might be too long. So my question is, did you try to employ shorter dwell time? つまり1時間に何カウントかというふうに見るのはですね、すごく平均化されてしまってニュートロンのバースが見られない。でもっと短いドウェルタイムでの実験をやられたことがあります。
Data sampling is 4 minutes. 4 minutes. One time sample.
4 minutes.
Your dwell time is
4 minutes.
dwell time.
Any other questions or comments?
I'd like to ask about standard deviation again. According to your report, you said the standard deviation was 3 sigma was 4 watt nearly, but I think it's very large. I wonder what is the main factor contributing to such a large 3 sigma level?
forward. But about Three Sigma is a lot forward.
Yes.
Yes.
But I think it's very large.
Very large, but we made that expression rather conservatively. But
it was caused by fluctuation of flow rate or
yes,
the
flow
noise.
rate and temperature measurement.
So everything is
fluctuations.
everything is contributing roughly
Yes,
equally.
yes, yes. We will superpose towards the contribution into Gaussian distribution.
I see.
Yes,
So since the time is coming, so I have to finish the discussion. So I would like again to thank all of the speakers. Thank you.
Thank you very much, ladies and gentlemen, for attending this morning's session. Lunch will be served in the restaurant Layla on the second floor, and the post previews for today will start from 2 o'clock again in this room. Also for tonight from 8 p.m. there will be special sessions by Dr. Tsarat on cold fusion activities in Russia, and Dr. Srinivasan will speak about the current activities in India. We sincerely look forward to your attendance there as well. Thank you very much.